Right now, while you watch this video, there's a storm raging on another planet that has not stopped for over 350 years. An ocean of liquid metal is churning beneath a surface no human will ever walk on. And somewhere in our own cosmic backyard, a world has been knocked completely sideways by a catastrophe so violent that scientists still cannot agree on what caused it. We were taught to think of the solar system as calm, the sun in the middle, the planets orbiting politely, everything quiet and orderly like a diagram in a textbook. That picture is a lie, or at least a comfortable simplification, because the truth sitting just beyond Earth's atmosphere is a neighborhood of extremes that makes almost anything we experience here look gentle by comparison. There are worlds close enough to touch with our instruments where metal would melt in your hand. Planets so massive their gravity bends the path of the sun itself. Places where the ground still carries the scars of impacts that rewrote a world's entire future in a single afternoon. And regions so hostile that humanity's most advanced machines arrive only to slowly die there. And here's the part that should genuinely unsettle you. None of this is ancient history. It is happening right now, in this instant, while you sit there watching a screen. Storms the size of continents are still rotating on distant gas giants. Lethal radiation is still streaming silently through space. A planet's interior is still cooling from a collision that happened billions of years ago, and we are only now starting to understand what that collision actually did. Over the next 18 minutes, we're going on a tour of 5 worlds that will permanently change how you see the solar system. Starting with the planet everyone dismisses as a boring, scorched rock, a world that turns out to be hiding ice and eternal. Darkness and a metal heart still beating beneath its crust. Then we move to the true monster of the system, a planet so enormous it doesn't even orbit the sun the way you think it does, a world whose storms have outlived empires. Then we visit the planet that simply refuses to follow the rules, tipped over on its side in a way that still has no fully agreed explanation. Then we drop down to the planet humanity has bet its future on, a world of frozen beauty hiding an invisible killer in plain sight. And finally, we travel to the very edge of everything we know, a tiny world billions of kilometers from the sun that recently forced scientists to rewrite the rulebook on how planetary atmospheres actually work. Buckle in, because this is not the solar system you learned about in school. For most of human history, Mercury was almost invisible to us, and not because it was far away. In fact, for long stretches of time, Mercury is statistically the closest planet to Earth, closer than Venus, closer than Mars. The problem is that it lives dangerously close to the sun, which means every time we try to look at it, we're staring almost directly into a star bright enough to blind our instruments and our eyes. For thousands of years, it was nothing more than a faint smudge crossing the sky. Then we tried to actually reach it, and that's when things got genuinely terrifying for engineers. Mercury completes a full orbit in just 88 days, 4 times around the sun for every single trip Earth makes, which means any spacecraft chasing it has to move at absurd speeds just to catch up. And the closer you get to the sun, the more the sun's gravity wants to simply swallow you whole. One small miscalculation and a multi-billion-dollar spacecraft becomes a fireball. In 1973, NASA gambled anyway, launching Mariner 10 on a trajectory so complicated it had never been attempted before, slingshotting off Venus's gravity just to bend its path toward Mercury, the first spacecraft in history to use a planet as a gravitational springboard. When the images finally came back, scientists braced for something boring, a smaller, more battered cousin of our own moon. What they found instead was stranger. Yes, the cratered gray surface was there, including a scar so massive it's called the Caloris Basin, an impact zone larger than entire countries on Earth. But then, they noticed something that made no sense at all. Enormous wrinkle, like ridges crossing the planet, some nearly 2 miles high and hundreds of miles long, as if the entire world had shriveled like fruit left out to dry. Nothing like it existed on the moon. And then came the discovery that broke the existing model of how small planets were supposed to work. Mercury has a magnetic field, a real one. Scientists had assumed a planet this small should be geologically dead inside. No churning molten core, no magnetic shield, nothing. Mars doesn't have one. Venus doesn't either. But tiny Mercury does, which meant something massive and alive was still moving deep beneath the burned gray crust. It would take another mission. The Messenger probe launched in 2004, taking nearly 7 years and a dizzying sequence of gravity. Assisted loops past Earth, Venus, and Mercury itself, just to slow down enough to enter orbit, to reveal exactly how strange this planet really is. Mercury's iron core, it turns out, takes up 57% of the entire planet's volume. Earth's core, by comparison, occupies only about 17%. Mercury is essentially a giant metal heart wrapped in a thin shell of rock, and part of that heart is still molten. But the discovery that genuinely stopped scientists in their tracks came next: ice. On the planet closest to the sun, In craters near the poles that never see a single ray of sunlight because Mercury barely tilts on its axis, water ice has been sitting frozen in absolute darkness for billions of years, a natural freezer hidden inside one of the hottest places in the entire solar system. And even now, after decades of study, there are features on Mercury's surface that nobody can fully explain. Shallow, bright patches scientists simply call hollows, as if parts of the ground are slowly evaporating into space on a planet that's supposed to be geologically dead. Some researchers now suspect Mercury wasn't always this brutal furnace. It may once have looked far more like early Earth, with more volatile compounds, more geologic activity, maybe even surface water, before violent impacts, gravitational tugs, or the slow aging of our own sun burned it down into the husk we see today. And that's the detail that should really sit with you, because billions of years from now, as the sun begins its slow transformation into a red giant, Mercury will be destroyed first, then Venus, and then Earth will become the planet closest to a dying, swollen sun, our oceans. Boiling away, our atmosphere stripped, our blue world potentially ending its life looking disturbingly like the silent, scorched planet we just described. Mercury isn't just a strange neighbor. It might be a preview of our own ending. Now picture something far larger, far more violent, and somehow also the reason any of us are alive to make this video at all. Jupiter sits roughly 5 times farther from the sun than Earth does, and yet it's still bright enough to be the third most visible object in our night sky after the Moon and Venus, but the brightness barely hints at its real scale. Jupiter's diameter is about 11 times Earth's, and its mass is 318 times greater. If you gathered up every other planet in the solar system and threw them onto a cosmic scale together, Jupiter would still outweigh them all, combined by 2.5 times. This is so extreme that Jupiter doesn't actually orbit the center of the sun the way you'd expect. The sun and Jupiter both orbit a shared point of mass called the barycenter. And because Jupiter is so massive, the point sits outside the sun's own surface. In other words, Jupiter makes the sun wobble through space. Its gravity is so dominant that it shreds, redirects, or simply swallows asteroids that wander too close, which is part of why it commands dozens of moons, at least 67 confirmed, many likely captured wanderers from elsewhere in the solar system. Some scientists believe Jupiter's gravity may have torn apart entire protoplanets in the chaos of the early solar system, or prevented others from forming at all, and that influence hasn't stopped. Over billions of years, Jupiter's gravitational pull may be slowly destabilizing Mercury's orbit, with one possible far future outcome being Mercury colliding with the sun or getting flung out of the solar system entirely, caused by a planet that isn't even nearby. But here's where the woo worked. Story flips. The same gravity that destroys also protects. Without Jupiter acting as a kind of cosmic vacuum cleaner, comets and asteroids would pass through the inner solar system far more frequently, and Earth's odds of catastrophic impacts would be dramatically higher. Many scientists believe that without this gigantic, violent neighbor quietly sweeping debris out of our path for billions of years, complex life on Earth may never have had the stable, undisturbed conditions it needed to survive. If you could dive toward Jupiter, you'd never hit a surface, because there isn't one. You'd fall through endless layers of churning clouds just 30 miles thick on the visible layer, mostly ammonia crystals, colored by chemical compounds called chromophores that react with ultraviolet light to paint those famous orange, white, and red bands. Those bands aren't just beautiful, they're war zones, with violent turbulence erupting at their borders, including the planet's most famous resident, the Great Red Spot, a storm large enough to swallow Earth whole, first observed in the 1600s and still raging today, although it has been visibly shrinking and changing color for decades, a centuries-old hurricane that somehow isn't even stable. Between 1998 and 2000, 3 smaller storms merged into a second one, nicknamed Red Spot Jr., smaller but still ferocious, orbiting close to its larger sibling and somehow avoiding a direct collision. Keep descending past the clouds and the pressure becomes so extreme that hydrogen, the lightest, simplest element in the universe, stops behaving like a gas entirely. It becomes liquid, then something even stranger. Metallic hydrogen, an electrically conductive metal ocean stretching through most of the planet's interior, generating a magnetic field 14 times stronger than Earth's, the most powerful in the entire solar system. Below that lies a core that remains one of the biggest mysteries in planetary science, because the pressures down there are simply impossible to recreate in any laboratory on Earth. And despite being made almost entirely of hydrogen, the very fuel that powers stars, Jupiter never ignited because it would need roughly 75 times more mass to trigger nuclear fusion. It got close. Not close enough. Around this giant orbits a miniature solar system of its own, including 4 enormous moons known as the Galilean moons, one of which, Ganymede, is actually larger than the planet Mercury. But surrounding all of it is an invisible radiation belt so intense that any human exposed to it wouldn't survive long, with the moon Io-bathed in lethal radiation every single day. And yet that same dangerous magnetic field also creates something stunningly beautiful, channeling solar particles into massive auroras at Jupiter's poles, curtains of light dancing across a world built entirely out of extremes. The most violent, most dangerous planet in our solar system might also be the very reason life on Earth got the quiet, undisturbed conditions it needed to survive. Now we move to a planet that simply doesn't play by the rules. Every planet in the solar system spins more or less upright relative to its orbit. Jupiter tilts only 3 degrees, Neptune about 28. Uranus tilts 98 degrees, meaning instead of spinning like a top, it essentially rolls around the sun on its side. For decades, the leading explanation was simple. One catastrophic impact, early in the solar system's violent youth, from an object possibly 1 to 3 times Earth's mass, slamming into Uranus with enough force to knock the entire planet over. Simulations in the early 90s seemed to support it. But there was a glaring problem. If an impact that violent really happened, Uranus's moons should have been thrown into chaotic, scattered orbits or destroyed entirely. Instead, they orbit in nearly perfect, stable circular paths aligned with the planet's tilted equator, as if the catastrophe never touched them. That contradiction turned a strange mystery into a genuinely unsettling one. In 2012, astronomer Alessandro Morbidelli proposed something bolder. What if Uranus wasn't hit once, but twice, the first impact beginning the tilt and destabilizing the disk of gas and dust around the planet? The second finishing the job, all of it happening early enough that the moons we see today actually formed afterward, out of the wreckage, which is why they look so calm now. Simulations showed 2 impacts totaling around 1 Earth mass could explain it, but that still didn't explain everything. Uranus's magnetic field is tilted 60 degrees off its rotational axis and is bizarrely offset from the planet's center, as if someone shoved its magnetic heart sideways. And stranger still, Uranus is far colder than it should be. Every other gas giant radiates more heat than it receives from the sun, leftover energy from its formation. Uranus barely radiates any internal heat at all, as though something switched off its furnace. In 2018, physicist Jacob Kegereis ran supercomputer simulations with over 100 million particles, testing more than 50 impact scenarios, and found that an object roughly twice Earth's mass striking Uranus at a precise 30 to 45 degree angle wouldn't just tip the planet. It would create a dense, scorching layer roughly 12,000 miles beneath the surface that acts like an insulating blanket, trapping heat inside and potentially explaining both the cold exterior and the chaotic magnetic field, caused by uneven pockets of rock and melted ice left scattered through the interior. But the perfectly stable moons remained unexplained until astrophysicist Mullane Salenfest proposed something completely different. Maybe nothing collided with Uranus at all. Maybe a massive moon, slowly drifting away from the planet over billions of years, exactly the way our own moon drifts from Earth, created enough gravitational tug-of-war to gradually tip the planet's axis through a mechanism called spin-orbit resonance, small pushes accumulating like someone repeatedly pumping a swing at exactly the right rhythm. Until at roughly 80 degrees of tilt, the system would become unstable. The moon's orbit would spiral into chaos, and it would eventually crash into the planet and disappear forever, leaving the tilt behind as the only evidence it ever existed, which would also explain why Uranus, unlike Jupiter or Saturn, has no single dominant giant moon today. We still don't know which explanation is correct, and that uncertainty might be the most fascinating part of the entire story, because it means our solar system's formation may have been far more violent, chaotic, and unpredictable than we ever assumed, and that the calm, stable system we live in might be the exception, not the rule. For decades, Mars was sold to us as humanity's backup plan, the next great frontier, a place where we'll build cities when Earth can no longer hold us. And maybe that future really is coming. But there's an enormous gap between visiting Mars and surviving on it. The atmospheric pressure at its surface is less than 1% of Earth's at sea level, roughly equivalent to standing far above the summit of Everest without a pressure suit, a death sentence within minutes. Average temperatures hover around minus 60 degrees Celsius, plunging past minus 120 at night in some regions, cold enough to freeze exposed equipment almost instantly, and even on relatively warm afternoons near the equator, heat escapes into space the moment the sun sets because the atmosphere is too thin to trap it. Water ice exists in huge quantities beneath the surface and at the poles, but liquid water can barely exist at all. The pressure is so low it either freezes solid or evaporates directly into vapor almost on contact. Worse than any of this is the threat you can't see. Mars lost its global magnetic field billions of years ago, and without that shield, solar wind has spent eons stripping away its atmosphere, while cosmic radiation bombards the surface unfiltered every single day, energetic enough to tear through biological tissue, damage cells, and corrupt the molecules that make up life itself, which is exactly why serious plans for human bases on Mars involve burying habitats underground rather than building on the open surface. Mars also carries scars from a far more violent past, including Olympus Mons, the largest volcano in the entire solar system, its base, roughly the size of a small country and its peak rising over 12 miles, tall enough that on Earth its summit would punch through most of the atmosphere, alongside Valles Marineris, a canyon system stretching nearly 2,500 miles, deep enough in places to swallow 7 kilometers, a scar so large that on Earth it would cross entire continents. Even today the planet stages dramatic, sometimes planet-engulfing dust storms that can blot out sunlight for weeks or months at a time, crippling solar-powered equipment and burying future missions in choking red haze. And yet, threaded through all of this hostility is one of the most tantalizing mysteries in modern science. Ancient riverbeds, deltas, and minerals that could only have formed in the presence of liquid water suggest Mars once had lakes, possibly even oceans, a planet that may have looked startlingly Earth-like billions of years ago. That possibility is why rovers like Perseverance are combing through Jezero Crater, an ancient lakebed, hunting not for animals or ruins, but for the faintest chemical fingerprints microbial life might have left behind, while intermittent traces of methane in the thin atmosphere, a gas often tied to biological activity here on Earth, keep the question agonizingly open. Mars is simultaneously a warning about how fragile habitable worlds really are, and one of the greatest adventures humanity has left to attempt. And finally, we travel more than 5 billion kilometers from the Sun to a world many people had already written off as a frozen, lifeless dot. When NASA's New Horizons spacecraft flew past Pluto in 2015, after a 9-year journey that had to launch by a strict deadline in January 2006, or risk arriving too late after Pluto's thin atmosphere had already frozen and collapsed onto its surface, it revealed something nobody expected: towering mountains of water ice, flowing glaciers of nitrogen and methane, and a delicate blue-tinted haze extending over 300 kilometers above the surface. But that haze was far colder than any model predicted, off by roughly 30 degrees. An inconsistency that nagged at planetary scientists for years. In 2017, a researcher proposed a radical idea. What if it wasn't the gases controlling Pluto's temperature at all, but the haze itself, tiny solid particles absorbing sunlight and re-emitting it as infrared heat that escapes efficiently into space, actively refrigerating the entire atmosphere from above, a mechanism nothing in our existing models accounted for. No instrument on Earth or in orbit at the time was sensitive enough to test it until the James Webb Space Telescope launched in 2021, and in May 2023, a team of astronomers finally separated Pluto's faint thermal signature from that of its moon Charon for the first time in history. What they found? What confirmed the theory completely. Pluto's infrared glow was stronger than its icy surface alone could produce, meaning something above the ground was actively radiating heat. And when researchers modeled the combined contributions of reflected sunlight and atmospheric emission, the predicted total matched the observed data almost perfectly. Pluto's haze isn't just floating scenery, it's the dominant force controlling the planet's climate, a discovery that upends decades of assumptions that gases alone govern planetary temperatures, and the implications stretch far beyond one small distant world, suggesting that Saturn's moon Titan, Neptune's moon Triton, and potentially countless distant exoplanets shrouded in haze may follow entirely different climate rules than the ones we've built our models around, possibly even echoing conditions on early Earth itself more than 2 billion years ago, before the planet's atmosphere filled with oxygen, when a haze, not unlike Pluto's, may have helped set the chemical stage for life to begin. After everything we've just walked through, it becomes hard to look at the solar system the same way again. We tend to assume Earth represents the normal case, the baseline, and everything else is the exception. The truth seems to be the opposite. The universe appears to prefer extremes: frozen wastelands, radiation-soaked deserts, gas giants locked in centuries-long storms, worlds physically knocked sideways by violence we still can't fully explain. Mercury showed us what happens to a planet that lives at the mercy of its star. Jupiter showed us a gravity so powerful it can both destroy and protect an entire system. Uranus reminded us that some of the biggest mysteries in the cosmos are sitting in our own backyard, unsolved. Mars showed us how a once promising, possibly habitable world can lose its defenses and become something close to unsurvivable. And Pluto proved that even the most distant, forgotten corners of our solar system still have the power to rewrite the textbooks. The more dangerous these worlds reveal themselves to be, the more captivating they become, because every discovery brings us one step closer to understanding how planets are born, how they change, and sometimes how they slowly die. The solar system is stranger, more violent, and more extraordinary than anyone ever imagined. And in the end, when we study these terrifying worlds scattered across the dark, we're not just looking at other planets, we're reading different chapters of the same cosmic story that eventually produced Earth and produced us.